also the University of Wisconsin-Madison. So with that, I'll turn over to Susanna and let her get started with an introduction. Thank you so much.
Hi, everyone. I'm excited to be here. So as Zoe said, I'm her colleague at the University of Wisconsin-Madison. I'm in both the chemistry and astronomy departments, and my group studies astrochemistry, specifically looking at the formation of prebiotic molecules. So we do a combination of laboratory spectroscopy, most of which is rotational spectroscopy, because that gives us the ground truth to then compare to observations using radio telescopes. And then for our observational work, we do observations of star and planet forming zones. And so we compare the spectra that we take of small organic molecules in the lab to the spectra that we take from telescopes of the gas phase chemistry in star forming regions. And we try to understand how that chemistry evolves as stars and planets form, and how the ingredients for life might form in these star forming regions in space and then be delivered to a planet. Um, in addition to that, we've started to branch out a little bit. So Ruby will talk about our new method where we combine rotational spectroscopy with infrared spectroscopy and mass spec so that we can form an ice, process it like it would be processed in the interstellar medium, and then look at what comes off of the ice into the gas phase. And then Hao is actually working on a new project where we're studying the formation of radicals that are applicable to the atmosphere of Titan, and specifically looking at small organic molecules there and what that chemistry might be. So with that, I want to turn it back to Zoe so that she can introduce my students, Ruby and Hao, and thank you all for coming.
Awesome. And thank you for the brief introduction, Susanna. That was wonderful. All right, so our first talk today is going to be Ruby Neisser, who is a second-year graduate student at University of Wisconsin-Madison in the Widicus Weaver group. Her research focuses on using infrared spectroscopy, mass spectrometry, and rotational spectroscopy. That's a lot of spectroscopy. That's awesome. To investigate the chemical pathways in interstellar ice analogs subjected to UV radiation and thermal processing. And before coming to UW-Madison, Ruby was at William and Mary and got a BS in chemistry, and she worked in the Kidwell lab there, working on the structure and photochemistry of atmospherically relevant molecules using laser spectroscopy techniques. So with that, Ruby, feel free to go ahead and share your slides and take it away. We see your
Okay, can you
slides,
all
so you're
hear
good.
me and see my slides?
Yes.
Okay, lovely. I'm going to minimize this really quick and then. Okay, so today I'll be talking about Sublime, which is the instrument here that we have at the University of Wisconsin-Madison, the sublimation of laboratory ices with millimeter/submillimeter experiment. As Zoe said, I'm a second-year graduate student, so I'll be talking about some of my initial results that I have. I'll also be touching on some of the results of my colleagues. Again, my name is Ruby Neisser, and I am a second-year graduate student. I'm in the PhD program, working towards a PhD in chemistry. And I know that there's a variety of different backgrounds in the audience here, so I'm going to try to give a bit of a broad overview of astrochemistry motivations, if for any biologists or geologists, just to make sure that we're all on the same page as to why we're doing this. So I'll start off with some motivations. Why are we studying interstellar ice analogs? Then I'll move into the experimental setup of our Sublime instrument. And finally, seems that we're missing. Oh, I'll talk about some of the projects that are happening in our lab. I'll touch on a few of my colleagues' projects, and then I will move more into my own, my preliminary results of the research that I am working on currently. Okay, I think I have to click. So to start off, why are we studying, what are complex organic molecules in space? Why are they of interest? So until relatively recently, as I'm sure many of you know here, it was thought that complex species there wasn't a lot of interesting chemistry happening in interstellar space. So it's pretty incredible that we see molecules in interstellar space, but we have observed upwards of 320 molecular species, according to CDMS currently, primarily with rotational spectroscopy. And I'll be talking about prebiotic molecules. This is a somewhat nebulous definition in the field, but they're molecules that are of interest for the formation of biological processes. So one example would be the precursors to amino acids. And as I'm sure many of you know, amino acids can undergo condensation reactions, forming peptides, which are the building blocks of proteins. So understanding the pathways towards amino acid formation via those precursor molecules is vital to understanding pathways towards larger biologically relevant molecules. And there is evidence based on meteorites that the isotopic ratios indicate that some prebiotic molecules actually formed in cold environments analogous to interstellar conditions. So that's why I'm focusing on interstellar space. Radio astronomy is the major detection method for a lot of these molecular species, and that is primarily for gas phase detection. And James Webb is the infrared telescope recently released, which allows us to peer deeper into molecular clouds and also observe these ices, not just in the gas phase, not just the gas phase species. So how are complex organic molecules formed? There's a lot of research dedicated to gas phase species, as my colleague Hao will talk about, and also a lot of modeling efforts. But the modeling predicts a lot fewer molecular species formed. The abundances are lower than what we're actually observing. So a lot of researchers have turned to looking at dust and the icy mantles that can form on the outside of dust as potential formation mechanisms towards complex organic molecules. Here I have a diagram of the general life cycle of the cloud going into a protostar, and I'll touch on that and relate it more exactly to our experiment in a moment. So interstellar ices, to back up a little bit, we have a molecular cloud. Within a molecular cloud, a cold molecular cloud, you can get these icy mantles forming on dust grains. This is primarily due to small molecules going from the gas phase and combining on these ices in a variety of mechanisms. And at cold temperatures, it's a lot of hydrogen mobility, because that's primarily the molecule that's mobile at such cold temperatures. This is a lovely graphic from Oberg et al. Chemical Review in 2016, showing the relative abundances of the simple molecular species in these ices. So the ices are primarily composed of water with decreasing amounts of CO2, CO, methanol, ammonia, and methane. Now, in these molecular clouds, in the interstellar conditions that I am looking at in particular, these ices can encounter a variety of different irradiation from interstellar sources. So primarily what I focus on is UV radiation, though there are other types of irradiation that the ices can experience, such as cosmic rays or electron bombardment. But here, UV radiation. So at the edges of the cloud, it has a lot more irradiation, primarily from the interstellar radiation field. However, even in the more protected parts of the center of the cloud, these ices can encounter UV radiation via secondary UV radiation, where cosmic rays interact with either the dust grains or molecular species present in the cloud and emit secondary UV radiation. Also, thermal warming. So as these clouds start to condense, they warm, and also once the protostar has formed, it will warm the surrounding gas. So thermal heating is another mechanism of molecular formation that we investigate here in our laboratory investigations, because of it has an analog to interstellar processes. This is the instrument that we use, just to touch base with a real image and our pretty UV lamp, which is pink. Now, to start off, we have this UV lamp. It's a microwave discharge hydrogen flow lamp, and it emits primarily in the Lyman alpha region, which is an important emission line in interstellar space. So it's analogous to interstellar conditions. However, it does have some emission at higher wavelengths, at around 160. Now, the take-homes about our experiment setup is that we have three methods of detection. We have FTIR, so Fourier transform IR spectroscopy, which we can monitor what we are depositing in our actual ice, which are deposited via gas lines. So we can input the species we want to look at via gas lines, and we can cool this window down to 9 Kelvin with a closed cycle helium cryostat, which I'm not sure if you can see my mouse, but this is the cryostat here. And that allows us to reach really low temperatures, which are analogous to the conditions present in the middle of a cold molecular cloud. So we can get down to 9 Kelvin, form an ice, and monitor what's happening in the solid ice that we formed with FTIR. We can also look at, you use a QMS to look at what's happening in the gas phase. The QMS, quadrupole mass spectrometer, allows us to monitor mass to charge ratios to look at the molecular species formed in the gas phase. And then one component that's particularly unique to our setup is the millimeter submillimeters component, which allows us to do rotational spectroscopic analysis on the gases that either desorb or sublimate from our ice. And these three detection methods are really important because they are complementary to each other. So FTIR is really important because we're able to monitor what's happening in our ice, but there's a lot of overlap between organic species. And the QMS is also a very useful and powerful tool. However, it is not very specific because there's a lot of overlap between different fragmentation patterns of molecules. So the millimeter submillimeter source is vital for having a lot of specific molecular identification, and its specificity is unmatched by these other methods, but the interplay between the three detection methods is what's interesting and important here. Now, this is an image of what's happening inside of our chamber to touch base with reality as opposed to that diagram. So here you can see the KBR window, which is transparent to IR light and allows us to do transmission spectroscopy of our ice, and the gas lines, which are pointed towards the window so we can deposit the desired species onto the window, and that cryostat, which cools down the window to approximately 9 Kelvin, and our UV waveguide, which is guiding that Lyman alpha microwave discharge hydrogen flow lamp radiation towards our sample so that we can irradiate the ice for the desired amount of time. Another important note is that we have ultra high vacuum conditions, which we're able to achieve with this turbomolecular pump system, and we can get down to 10 to the negative 11 torr. This is useful for considering astrochemical conditions and trying to replicate what's happening in these interstellar environments. Now I'll talk about the general procedure of the types of experiments that we do. There are variations with this between different experiments in our lab, but this is the general procedure. So we start by depositing the ice. We can cool that window down to 9 Kelvin, input them in the gas phase, and form an ice of our desired composition, and monitor that with our FTIR. This is an example from my own experiments of I'm doing water, ammonia, and carbon monoxide ices, and you can easily see the different vibrational modes present in the ice, and this is useful for quantifying the relative amounts of each species present in the ice. Second, we tend to do irradiation with our microwave discharge hydrogen flow lamp to represent the irradiation encountered in the interstellar conditions. The time at which you irradiate this ice depends on what your goal is. So the general rule is that about 30 minutes for a 0.1 micron thick ice will be equal to the amount of irradiation that an ice would experience in the middle of the cloud in about 500 years. But excuse me, at the edge of the cloud at about 500 years, but in the middle of the cloud about 10 million years. So essentially, it depends on where in the cloud you're trying to replicate and what interstellar conditions you're trying to replicate. But the flux that our UV lamp emits is much higher, so it's shorter amounts of time are analogous to long times in space is the take home there. And this is an example of my own experiment where you can see CO2 forming even at 10 minutes of irradiation due to oxygenation of CO primarily. Finally, TPD, this stands for temperature programmed desorption. Generally, you heat your ice sample until all of the species have sublimated away into the gas phase, and you're left with a clean spectrum. However, if you form more complex organic molecules, as you'll see one of my colleagues has, those there will still be some residual organic species present on the window. Your ramp rate also depends on what experimental parameters you're looking at. In my experiments, I used 2 Kelvin per minute, but it allows you to observe at each temperature what is present in your ice, what is present in the gas phase, and allows you to kind of disentangle what's happening during the course of interstellar warming and figure out what species are present in your ice. And this is an example of the QMS TPD profile of water, just for a demonstration. And as you would expect, water sublimates around 160. This is verified by other sources as well. Now, I'll speak briefly about the rotational spectroscopy component as well. The general setup, this is just, now I'll be talking about the millimeter, submillimeter to electron bolometer observational detection method here. This is the general setup, well represented in other labs or in other laboratory setups to do rotational spectroscopy. We have a synthesizer and multiplier chain that allows us to achieve the desired frequency of light for analysis, lock-in amplification system, and detection with an electron bolometer. And I put an example spectrum here on the computer, just of the general, but I have not obtained a lot of rotational data yet, because I want to establish what's present in the ice with IR and QMS to do some targeted searches in the future. I guess my ordering is a bit off, but here, just to touch base, the power of rotational spectroscopy in this experiment is that it gives specific unambiguous molecular identification, whereas there's a lot of overlap in the IR signatures as well as the QMS signatures. The experimental procedure for doing the rotational spectroscopy analysis does require us to close off our turbo for a little bit, so that we're able to obtain enough pressure to observe it with our in the gas phase. And the potential results of doing the rotational spectroscopy analysis is that we can do targeted scans. So I plan on doing some targeted scans looking for formaldehyde and other specific species. And you can identify based on previous data where those rotational transitions should be and look to see if they're present in the gas phase during the course of TPD. You can also do broadband scans, which is useful if you are trying to identify species that you might not expect to be present, but then you can do comparison. The analysis and disentanglement of those broadband spectra are tricky, but very useful. And also, this is analogous. The rotational spectroscopy data obtained would be directly comparable to rotational spectroscopy observational spectra with tools like ALMA, for example. Now, I'll quickly highlight some of my colleagues' work. So my colleague Alejandra is working on a project combining water, CO, and methanol ices and in varying compositions. She has started to make a lot of production plots where you can track the production of certain molecular species during the course of irradiation and looking at how the relative amounts of methanol and carbon monoxide contribute to the formation of these different species. This is integral and very important for understanding the chemical formation pathways of these molecules present in the ices, both during irradiation and during TPD. And also here is proof of some of the power of our experiments for comparison with infrared telescope data. So this is the comparison between her ice compositions and also a previous ice composition done in our lab and the infrared data obtained from near 38. Now, my colleague Catherine is looking at the effects of the microwave discharge hydrogen flow lamp parameters on the photo products and spectra of the ices. So in a lot of studies of ices, they use a microwave discharge hydrogen flow lamp. But even in investigations where they use the same ice composition, different labs are getting different photo products. So Catherine is investigating why, what investigating ways to account for these differences. And these are just a few of the parameters that are potentially at play here that can vary between the experiments. And Catherine has began, here's just an example of tracking the pressure of hydrogen gas in the lamp and how that affects the photodegradation of methanol and the photoproduction of CO. The take home here is that properly characterizing the UV spectrum of the lamps is really important for comparison, for accurate comparison between different investigations. And my colleague Colette is using a novel approach looking at simultaneously irradiating the ices and warming. So as I said before, usually you do irradiation followed by TPD. This is useful for disentangling what products are formed from UV radiation versus what are formed from warming. However, in interstellar conditions, while the cloud is condensing or the protostar is warming the gas, it's still being irradiated by UV light. So looking at the potential products of doing these at the same time is useful for mapping onto actual interstellar processes. And she is looking at ices composed of methanol and water and varying compositions. Here, one of the interesting components about her investigations is she has, even upon warming to 300 Kelvin, she still sees organic products left on the window. This is an example of the spectra, the residual spectra, so what's present even after reaching room temperature of varying percent methanol. So with water and methanol, here the 100% is 100% methanol, all the way down to 0.1% methanol. So more methanol tends to create more of these residuals, but I won't speak too much to the different products that she has been forming and her different experiments, but she is doing some normalization based on fluence. Now to my own investigations. I think I mentioned before, I'm looking at combining water, ammonia, and CO ices in various compositions. I'm focused on trying to keep my molecular compositions within the realistic parameters that have been observed in these ices. So water is the largest abundance molecular species that has been observed in the ices. So normalizing based on water, and then CO is the next most abundant of my molecular species, and then ammonia. So I generally want to have an ice that's dominated by water with about 30% CO and about 10% ammonia. This is just achieved experimentally. Note that I'm using 50-50 solution of water and ammonia. This has to do with the vapor pressure, which is allows more ammonia gas to be deposited into the chamber. So just using the 50-50 solution allowed me to obtain a pure ammonia ice, which is important for establishing a baseline in order to quantify my data. Back to the spectrum, I'll speak a bit more. So here you're able, when analyzing IR data, I'm able to quantify the relative amounts of water, ammonia, and CO based on the integrated intensities under these different vibrational modes present in the FTIR. So the unique modes are particularly easy to quantify, and I have to do a bit more analysis to quantify my water, the amount of water, but you can utilize a derivation from the Beard-Lambert law and determine combined with previously determined band strengths to determine the relative amounts of molecular species present in these ices. The chemistry happening in mixed component ices is incredibly complex. And in cold ices, when there's just irradiation at play, it's primarily hydrogen that's mobile at such low temperatures. And here is just a few examples of the complex chemical pathways present. And my work is looking at trying to disentangle what is happening here. So I don't have any finalized reaction coordinate diagrams of what's happening, but these are just some examples. And I'm looking to track these pathways and figure out exactly what's happening in my ices with this 3-method detection setup that we have. One potentially interesting component of my research is maybe the potential for forming the prebiotic molecule immunomethanol, which is involved in the Stryker-type synthesis of glycine. There was a recent study where Singh et al. Showed that methanamine and ammonia can combine to make glycine. But immunomethanol is also at play in the potential formation of glycine, and it has been established in past studies that formaldehyde and ammonia can create aminomethanol. And it's known that, and I have produced some amount of formaldehyde in my ices, so I can't speak yet to conclusive determination of the formation of aminomethanol, but that's something that I'm looking into, and one of the potentially interesting prebiotic molecules that I'll be analyzing, or that I'll be searching for, or attempting to observe. This is an example of a difference spectrum, so subtracting out the initial spectrum of the deposited ice to look at change over time. And you can see that even at 10 minutes, you see the formation of the HCO radical, which is primarily thought to be formed via hydrogenation of CO, which makes sense considering I have CO in my starting ice. And then formaldehyde, which is primarily, although not only, formed via hydrogenation of that HCO. And there's two characteristic peaks that have been cited in past literature as being due to formaldehyde that I have observed upon irradiation of the ice. Now for the next stage of my experiments, which is that thermal processing with the temperature programmed desorption setup, you can see a lot more interesting species starting to form, but the IR has a lot of overlap in these regions, in these interesting organic regions. And then just proof of concept, we see that water sublimates away out of the ice into the gas phase and disappears by 180, as we would expect. This is confirmed by what we observe in our QMS data, monitoring water here in the blue at mass to charge 18, and you see the TPD profile showing it beginning to desorb early on, and then all of it being gone by 180, confirming what we see in our IR spectra. And then CO is the 28 mass. You see a large amount of CO sublimate away around 30 Kelvin, also confirmed by previous studies. But interestingly, you do see some 28 mass later on. That may be due to other mass to charge fragments that are at 28, but also because of the ice matrix effects of water, you can have some trapping of CO molecules within this ice so that they're not able to sublimate away until after the water and ammonia ices have also sublimated. This can be seen as well in the CO2 band. This is just one interesting component that I've observed and has been observed also in past studies, but I hope to analyze this a bit more in the future. But the CO2 peak around 2343 wave numbers begins to decrease towards 2339 as the water ice is beginning to sublimate. And that might be due to ice matrix effects or interactions with the water and ammonia molecules present in the ice. And I've started to do some mapping of the integrated intensities over time, both with irradiation and temperature of my initial ice components. And I'm also starting to look at the photo production of the products, and I will continue to analyze that. However, I'll just show what I have so far here for the ammonia ice. Upon irradiation, you see it start to decrease, and then warming, you see the ammonia, the sublimation of ammonia represented in the drastic decrease in absorbance. And this is a note that this is the relative amounts of water, ammonia, and CO are up in the corner. So the red is obviously the highest abundance of ammonia relative to the other species. And monitoring ammonia in the gas phase via QMS data. This is photo production of CO2 and the warming products of CO2, so the relative abundance during the course of warming as well. And I'm also attempting to do some multi-peak fitting for my IR data. This will obviously be interesting, will be complemented with rotational data in the future. So next steps, I want to perform more replicates of my different ice components and actually achieve all of the ice compositions I was looking to do. Doing rotational spectroscopy analysis, start doing targeted scans once I've compiled enough information about what I suspect is present with my IR and QMS data, particularly looking for formaldehyde because that's an important intermediate in a lot of the reaction pathways I'm interested in. And then doing integrated intensity tracking for those smaller species in the ice potentially doing multi-peak peak fitting. And with that, I'd like to acknowledge the Widicus Weaver Group, our funding sources, and the University of Wisconsin-Madison, as well as my amazing colleagues, Catherine, Colette, and Alejandra, among others. Thank you.
Awesome. Thank you so much, Ruby. That was fascinating. Okay, so what we're going to do is we're going to hold all of our questions until after Hal's talk. So thanks for that, Ruby. I'm sure there will be many questions that we'll address after that. So now we'll shift over and go to Hal's talk. So Holdson Haocheng Liang is a graduate student again at University of Wisconsin-Madison in the Widicus Weaver group. He received his BS in chemistry from California State Polytechnic University in spring 2021, and he is a recent winner of the NASA Finest Fellowship. Congratulations, that is awesome. And his current research is focusing on investigating prebiotic radical species using millimeter submillimeter spectrometer coupled with supersonic expansion high voltage discharge source. So Hao, anytime you're ready, go ahead and share your screen and take it away.
You guys hear me fine?
Yes, and we see your slides.
Thank you
too.
for the introduction. Good morning, everyone. Now let's shift a gear a little bit. Very different from the sublime experiment in our lab. My project focuses on probing prebiotic radicals in the interstellar medium using rotational spectroscopy. Because of the challenges of studying rotational species, radical species in the lab, my talk involves a lot of instrumental approach. But first, let me take you back to the bigger picture of our current research. So looking at all of the stages in the original of life research, our group focuses on the prebiotic synthesis. Prebiotic synthesis of organic molecules. These molecules eventually form biochemical building blocks such as amino acids, sugars, and nucleobases. They are hypothesized to have been formed during the star formation and delivered to the planets via asteroids, comets, and meteorites. Broadly speaking, our group seeks to answer the question, how are these prebiotic molecules formed via chemical reactions in the interstellar medium? And at what stage did biologically relevant chemistry emerge? To address this, we investigate in the chemistry in the interstellar medium and planetary atmospheres, where photochemistry is a main driving force. Radiation from the stars can photodissociate and photoionize molecules, producing reactive species such as radicals and ions. These species, having a lower reaction barriers, will drive further chemical pathways, leading to a formation of a range of complex organic molecules observed in the space. Today, more than 320 molecules has been detected in the interstellar medium, and many of which are radicals. Astrochemists use radio telescope to study the chemistry of the interstellar medium. And what I do specifically is to collect rotational spectra of potential molecules exist in the space and analyze their spectroscopic constants, which provides valuable information in guiding future astronomical observation. Specifically, we use millimeter submillimeter spectroscopy to collect this information. The millimeter submillimeter wavelength covers wavelengths between 15 micrometer to 1 centimeter. This in terms of frequency is between 30 gigahertz to 20 terahertz. A lot of work in astrophysics has been done in this range because many small molecules exhibit period rotational transitions in this range. These transitions are very valuable because they are structure specific. As you can see in this rotational energy level formula here, the rotational energy level is depending on the moment of inertia, which is unique for each molecule because the mass, the bond angle, and the bond length are different from molecule to molecule. And because of these, the rotational spectrum is like a fingerprint for each molecule when we search for these molecules in the space. By collecting and analyzing the rotational spectra of molecules, we can obtain a set of spectroscopic constants, which help to generate precise theoretical predictions of a molecule. This information will help the observations to target a specific frequency instead of doing a very broadband scan in a certain direction. And when we use, especially when we use telescopes like ALMA and NOEMA, our research will really help their observation. By matching the observed spectral line in the astronomical data, such as shown here in the gray color, to the laboratory measure or theoretically predicted spectra shown in purple here, we can see this matching really helps the astronomers to identify specific molecules in the interstellar medium or around planets. In addition, this information can be used to conduct Boltzmann analyses, allowing us to quantitatively determine the physical conditions such as density and temperature of the molecular clouds, providing valuable insights into how the history of these molecular clouds. So the spectrometer that we use is a direct absorption spectrometer. For those of you who are not very familiar with spectroscopy, we can take you back to your general chemistry or high school chemistry. We'll talk about Beer's law. Sorry, wrong picture. We'll talk about Beer's law here. This is a similar setup as as the spectrometer that you might have used in your general chemistry. Our spectrometer is housed in a high vacuum chamber. The pressure usually is 10 to 16 millitorr. While it's running, it can go up to 50 millitorr. We operate in millimeter submillimeter wavelength, and we couple this spectrometer with a high voltage discharge source and a supersonic expansion source to study the radicals. Here is a detailed schematic of our experimental setup. I will break it down and go through each pieces here. The first one I want to highlight is our needle style high voltage discharge source. This is how we produce the radicals in lab. Here we generate our high voltage from our high voltage power supply and send the high voltage through a pulse generator, which turns the high voltage into different pulses. And we will send it through a variable ballast resistor box to maintain the stability of our circuit. And finally, this high voltage pulse is sent to our discharge source, which looks like the picture on the upper right-hand corner here. And okay. This was supposed to be a video, but not sure why it's not working. But so you can see here, while it's running, it will produce a plasma here in our chamber. And a radical is a species that has at least one unpaired valence electron. The radicals are very chemically unstable, and they have a tendency to undergo rapid reactions with other species. So it makes it really challenging to study radicals because of high reactivity in the lab. An effective method to tackle this is by doing a supersonic expansion. As shown in the figure here, this is creating by forcing the gas to move from a region of high pressure to a lower pressure, which we have a backing gas line here, usually is loaded with very high pressure, while this side is our reaction chamber, which is around 10 to 16 millitorr. By forcing them to go through this small nozzle on the pulse valve, the most of its random thermal motion will be transformed into direct motion, which reduces the internal energy of the gas molecules, resulting in the cooling of the gas, as well as forming a zone of silence, which is a free flow region for the gas to flow freely, and they will become sufficiently spaced apart that no further collisions could occur. So although the radicals are very reactive, if they have a large mean-free path and there's no other molecules for them to pass this valence electron to, they'll remain stable for a good amount of time. And while we're running this pulse valve, we can, our plasma kind of line up this, the boundary of our supersonic expansion here. You can see it a little bit in this picture. Our pulse valve is what we use to create a supersonic expansion. The pulse valve is working by having a solenoid controls this spring here inside the pulse valve, which is connected to a pipette. And while we run the pulse route, the solenoid will keep pulling the spring back and forth, and this pipette will load and release the gas in this process. The pulse route is controlled by the pulse route generator here, which is also controlled by a delay generator to control the timing and the speed of the pulse route. Here we have a steel bubbler. This is what we loaded our gas to form the high pressure region. And on the other side is our experiment chamber, which is the low pressure region. And the way we use to generate our millimeter submillimeter wave is by using a microwave synthesizer here. We will generate our microwave signal, and then it will be sent to multiply by this Virginia dial frequency multiplier here. And this multiplier can multiply our frequency up to different frequency region, which we will be matching the ALMA from 70 gigahertz to 1,000 to 1 terahertz. Our signal detection is done by two different detectors. One is the zero bias detector, and the other one is in-speed Hall electron bolometer. What we usually use is the in-speed Hall electron bolometer because it provides a greater sensitivities. The bolometer is a thermal detector because it detects the incoming radiation with a piece of in-speed detector material. The in-speed material has a resistance that will change with different temperature. Thereby, by monitoring the change in resistance, we can detect the signal coming to the bolometer. And we'll amplify our signal using a lock-in amplifier as shown in the picture here. Lock-in amplifier can extract very small signals and improve our signal to noise ratio. So with all the experiments set up, the first step I will go is to optimize the pulse route position, because our experimental chamber is pretty large in size, and we need to ensure our light passes through the zone of silence to probe the molecules that we hope to probe. And what we do is we use a methanol line as shown here. We get our catalog file from clone data of molecular spectroscopy, clone database of molecular spectroscopy, and we simulate them at 20 Kelvin, which is what we expect to have in the zone of silence. And we adjust using this translation stage here to adjust X and Y and Z axis of our pulse valve. And what we're trying to do is we try to have this methanol spectrum to match what it would look like at 20 Kelvin. So if the spectrum on top here is when the pulse route is out of perfect position, and the spectrum down here is when the pulse route is aligned in a good position. And you can see here, our spectrum with methanol is aligned with the catalog line pretty well. And with this optimization, we'll go into what we actually interested in, which is methylamine. Methylamine is the simplest primary amine. It is a precursor to glycine, which is very important prebiotic chemically. And methylamine has been detected in many astronomical environments, such as multiple star-forming regions like Sagittarius B2 and Orion KL Nebula. It's also been detected in meteorites, and it's also been detected in atmosphere of Titan, which is closely tied to the NASA Dragonfly project. And this is also what our group recently get the funding for studying this project, is to investigate the methylamine dissociation pathway on Titan. So the photodissociation of methylamine, there are four major pathways. The first one is to form a CH3 radicals, and there could also be CH2NH2 radicals, CH3NH radicals, and CH3 anti-radicals. Our ultimate goal is to investigate all four major pathways of methylamine dissociation and study how this mechanism may lead to the formation of glycine, whether in interstellar medium or in a planet like Titan. So our first target is the CH2NH2 molecule. Just looking at this molecule, it has a lot of spectroscopy feature. It has a fine structure because it's a radical. It has a hyperfine structure due to the hydrogen atom and nitrogen atom inside. It has quadruple couplings because of nitrogen. It has magnetic hyperfine structure because the magnetic dipole moment of nitrogen. And there could also be hydrogen splitting because the 2 hydrogen on carbon and 2 hydrogen on nitrogen, depending on how they rotate, the hydrogen could be equivalent or different from each other. And on top of that, there are also 2 large amplitude motions, which are the internal rotation of this methyl group here, as well as the inversion of the amino group here. So the key takeaway for looking at CH2NH2 spectroscopy feature is that all of these will contribute to line splitting, meaning that one single line could split into tens of different lines and thereby adding a lot of complexity to the spectrum and also reduce the signal and the intensity of the peaks that we might observe. So we have a collaboration with Professor John Stanton from University of Florida. He's a theoretical chemist, so he employs high-level computational methods to provide to predict a rotational spectrum for us, which guides us to find these molecular transitions or spectroscopic peaks in our spectrometer. Here, I want to take you back in our history a little bit of this project. This project was initially started in Emory University back in 2019. And in 2020, our group relocated to the University of Wisconsin-Madison. And after a long period of COVID-19 pandemic, as well as a building shutdown in our department, we have a temporary lab space in 2020, where our group alumni, Connor Wright, detected 17 lines of CH2NH2. Here are the 17 lines that he detected. And using these information, he was able to fit the spectrum, which is in a simple word, in another word, is just to determine the spectroscopic constant. So you can see here the ABC rotational constants are determined with a certain level of accuracy. However, the distortion constants down here still needs a lot of improvement. And to do that, we just need to collect more spectral line, and the more data will help us to calculate and determine these spectroscopic constants better. And in March 2020, our lab started moving again, and we finally moved into our permanent lab space in August 2022. And here's where we started, a very nice brand new lab. And after 2 years, this is what it looks like right now. A lot of instrumentations, a lot of setting up has been happened. Now, with this instrument built, we really want to look at some of these CH2NH2 line to help us to get back on track on studying this molecule in the lab. So I picked 2 very strong and transitions here on the among the 17 lines that Dr. Connor Wright detected. And I dive in and did a round of search of lines, but there's no clear detections. As you can see here, these spectrums are very noisy and there's no obvious signals. So I had to take a step back and think about what could have been wrong. And there are just so many things that could have been wrong. Is the experiment set up working properly? So we use CH2NH2 as CH2NH as a benchmark molecule. It's a neutral molecule with strong catalog lines, so it should be very easy to observe in our setup, which turns out to be the case. I was able to find a CH2NH line, very strong line at 191 gigahertz. And with that line, I optimized some backing pressure using these lines and as well as the CH3NH2 lines. And the backing pressure is the pressure of the carrier gas, which can impact the supersonic expansion behavior. So what we found is our line intensity increases as the backing pressures increases up until our maximum output from our regulator, which is 100 psi. And at that time, we can see there's no significant increase comparing to the 90 psi, but we also can't go up high, go any higher anymore with our regulator. So we decided to just use 100 psi as our backing pressure. And after that, we also do optimization of our discharge source. So we investigate in different discharge voltage as well as discharge current to see how that might impact the high voltage discharge behavior, which in turns impact the radical production. We can see the higher the voltage and the higher the current, the more intense the signal. So what that tells us is that we want to turn our voltage and current as high as possible to increase the production of our radical. And then once again, is capped at 1.8 kilovolts and 60 milliamp because that is what our high voltage power supply can go up to. With that, we go into another round of CH2 line search. And this time we were able to find a signal at 196 gigahertz. And with subtraction, which is this red line minus this black line here, we can see this is what our signal looked like. And by comparing this to what Connor have found, you can see that this is a very good reproduction of what he has found with a similar spectroscopy feature. So over here, I was very excited and I thought, oh, success is within the reach. But my undergrad professor once said, there's no such thing as failure in the lab. There's only a lot of learning opportunities. But it turns out there are a lot of learning opportunities instead of success. There are some setbacks when I try to proceed to the next step. The first one is there a little success in line search over for other frequencies and other lines that Connor has been detected. And also because I turned on the voltage and current so high, the very high power and intense plasma, as well as the high temperature, destroy our pulse valve. So I have to take a step back and rethink once again. And when I present this in another conference, I was asked whether I consider Zeeman effect. Zeeman effect is a splitting of spectral line into several components because of the presence of a static magnetic field. The interactions between molecules unpaired electrons, which in our case we have an unpaired valence electron, and the Earth's magnetic field can cause the line splitting to our energy in our spectrum. And to examine if we have a Zeeman effect in our spectrum and in our setup in general, we put molecular oxygen into our spectrometer and we did a scan. And what the catalog file tells me is that there should be one oxygen line here, but what we really observe are two oxygen lines, meaning there is indeed a split in our oxygen line. So what we have to do is we have to neutralize these magnetic fields impacting our spectrum. By that, we were trying to build a Helmholtz coil which produce a region of nearly uniform magnetic field. It consists of two electromagnets in the same axis, but on all three axes will be 6 electromagnets, and it carry it'll carry an equal electric current in the same direction. And here's where I am right now. So just looking at the future work, there need to be more optimization, such as on the settings of high voltage discharge. What I have done before only consider the intensity of our spectral line, but ignore the experimental condition in our lab. So I still have to optimize the power and timing. And because we are dealing with a gas samples, we have to generate a lot of vapor pressure from a liquid sample, the liquid methylamine. So we also consider heating the temperature of this steel bubbler to bring up more vapor pressure, which is more sample for our spectrometer. And we also think about designing a different discharge source if needed. And what other instrument approach that we have is that we have a compact mass spectrometer in our lab that provides more sensitivity than our spectrometer. This mass spectrum has a detected limit of 5 times 10 to the negative 14 torr, and that can help to tell us whether this radical is actually produced, and help us to eliminate a lot of the potential possibility of why our experiment is not working. And one instrument approach is we can modify a flange on our chamber to add the RGA here. And it requires differential pumping. So I have this design drawing here. Another instrument approach that we can have is adding a cavity in our spectrometer. The cavity is a two parallel mirror that reflects the light back and forth between two cavity mirrors. And they increase the effective path lengths because the light just keep bouncing back and forth here, and improve the sensitivity and signal to noise ratio. Showing picture down below here is a cavity that we can make in our lab using a Teflon block with some copper tape, as well as some photoresist here. This technique is started by Dr. Liam Duffy at University of North Carolina, Greensboro. And I visit his lab to learn about how to make this cavity myself, and hopefully I can make a set of this cavity and apply to our chamber. So in summary, I reviewed
I'm not hearing Hao anymore. Hao, I think you might have muted yourself somehow.
Okay, thank you. Yeah, I am not sure.
Okay, yeah.
Can you hear me now?
Yes, we can. Awesome. It was
Okay,
just like
great.
maybe the last 30 seconds or so.
Yeah, I think I might have let go. Yeah, but in summary, I rebuilt the experiment setup at University of Wisconsin-Madison, optimize it, and try to search of our CH2NH2 lines. And more of our future bigger picture goal is we try to collect all different radical spectra in our methylamine photodissociation product, and we'll search for these radicals in observation and hope to understand their potential roles in formation of glycine. And what another benefit adding to this project is it can eliminate some of the interference of future spectroscopy projects by having more data around what methylamine can form. So with that, I would like to thank the entire Widicus Weaver group for their help in my research, and Department of Chemistry, as well as NASA for funding. I'd also like to thank Dr. Blaise Thompson and Steve Myers for helping me to put the instrument together. And thank you for your attention.
Wonderful. Thank you so much, Hao. That was fascinating. And wow, like what a lot of work into putting everything together and all the multiple moves that you guys have had over the years. So that's fantastic. All right, we are going to open the floor for questions now. So I'm going to start while everyone is thinking in the audience. First of all, you can feel free to either type those in the chat, or you can use the raise hand feature in Zoom, and then we can call on you to ask your question verbally. Maybe while you're thinking of questions, I'll start off with some of the questions that have come in already. So our first one came to Ruby, and AC asked, do you include any trace C13 to determine species variations from alternate kinetic reactions? And also wondered if any PAHs are generated in the system. Ruby, you're muted.
You're muted.
Sorry, can you guys hear me all right?
Yes.
So the question about trace C13 to determine species variation, I think you perhaps are referring to isotopic labeling of the input species, which I have not done. That is definitely a route that I'm interested in looking at to clarify those pathways. But if you're referring to like using the C13 as an isotope label, I have not done that yet.
Okay, awesome.
Oh,
Then we had, sorry,
apologize, I didn't answer the PAHs. So yeah, I'm still searching for the different IR signatures or product signatures in my resulting spectra. So I can't really speak conclusively to about PAHs. I have not seen any yet, but that doesn't mean that they're not there.
Awesome. All right, it looks like Shirshak raised a hand. Do you want to unmute yourself and ask your question?
Yes, I want to say something. In Ruby's experiment, that why we use the UV only radiation as the UV radiation. I mean that, as we know that the UV spectroscopy is limited, means it cannot be applied to solid or gaseous sample. Then for this problem, can we just replace this UV radiation with another radiation by having the same result?
So are you asking about like why we're only using UV radiation and not electron bombardment or other sources of irradiation?
Yes, quite like that. Because in UV radiation, the solid or the gaseous sample, we cannot measure it. Means the UV spectroscopy is limited.
So we're not taking a UV spectra of um our sample, but we are irradiating it with UV. So we're looking at the effects of UV irradiation with other spectroscopic methods like infrared, rotational, and mass spectrometry. So the motivation for UV is that we know that that's a source that is a source of radiation in interstellar conditions. There are other labs have done investigations using other radiation sources like ion bombardment, electron bombardment, or other sources, but that isn't part of our instrument currently. I mean, that could be a route to look at if I'm not sure I adequately answered your question.
Cool. Maybe you guys can follow up behind the scenes if there's further questions on that.
Yeah, if you have any follow-ups, I'd love to chat.
Yeah. Awesome. All right, we had another question in the chat from someone who then had to leave, so requested potentially a follow-up email, which I can provide to you, Ruby, later if you want. But their question was, why in particular do you choose the heat rate of 2 Kelvin per minute? If you change this rate, then what differences are expected or observed?
So I chose 2 Kelvin per minute primarily just I did that in my first few experiments, and keeping that constant across my different experiments is important for comparison. So just basically to have a constant one. 2 Kelvin per minute is moderately represented in the literature. I know some studies do 5 Kelvin per minute, some do 2 Kelvin. Some of my colleagues do 1 Kelvin per minute. Usually a slower ramp rate, it's easier to see the species desorbing. So I think if there's any ambiguity about sublimation temperature for a specific mass fragment, I think maybe doing a slower ramp rate may clarify that. But I have not done any investigations comparing the ramp rates. There are some differences, but mostly just it's a little bit easier to see the specific species going if you do it at a slower rate.
Okay, awesome. Then we have a question in the chat from AC. I'm guessing it's for Hao. Says, if your ionization discharge from a DC voltage source, will this also generate a magnetic field? And could you use an RF HV discharge to mitigate Zeeman splitting?
Yes. So if we use a DC voltage source, it will indeed generate a magnetic field. I haven't had a chance to investigate in this how strong the magnetic field would have been. There should be a calculation to calculate it. I never thought about it. But yes, we could also use a RF HV discharge to mitigate the Zeeman splitting, but the Zeeman splitting is mainly arise from Earth's magnetic field. When I do our molecular oxygen scan, it is in the high voltage discharge was not turned on, and I just flow molecular oxygen through supersonic expansion, and the line is ready, is zone splitting. So my current plan is to think about how to neutralize Earth's magnetic field, but this is a great question, which is something that I didn't take account into when I try to design this coil.
Awesome. Thank you so much. All right, do we have other questions from people in the audience? Maybe while they're thinking, I can ask a question or two. So Ruby, I was wondering about when you were talking about the timescales for the comparable irradiation between the lab and in the cloud. part of me, I'm just wondering, and I don't know if there's an answer to this question yet, but do you think that the very different timescales to get the same amount of like total flux, could that affect the chemistry in ways that we're not just aware of at the moment?
I
Or do you have
actually
thoughts on that?
I love that because I think that often. Yeah, I don't know the answer to that, but that is definitely something to consider. I think it would maybe just be a caveat to the products that we're seeing of, okay, if the, total irradiation time has this big factor of like we are rating it at much higher fluxes so that it is representative of longer times in space, how might that affect the chemistry? So I think that's certainly something to consider, but I don't have a concrete answer.
Yeah, fair. And that's kind of an evil question to ask because just like experimental, you can't irradiate something for 10 million years and wait and measure it. That would be a very long PhD, right? Yeah. Cool. Awesome. Any other questions from people in the audience? Let's see. I think I had another one for Hal. Yeah, I was curious about the methylamine and Titan project that you mentioned. Would you mind maybe speaking about that in a little bit more detail? Just like what are you trying to measure, or what are you excited about, and dragonfly, things like that.
Sorry,
I didn't hear your question.
Oh,
Because
sorry.
my phone just lagged now.
No problem at all. If it's a bad time, I can not ask my question, but
Oh,
I'll
that's
ask it again, and then you can tell me whether or not you want to answer it. So the methylamine and Titan that you were mentioning, this recent project from NASA, I was wondering if you could speak a little bit more about like what's the main objective of that, and what are you excited for, and how does it relate back to Dragonfly and what it's going to potentially see there?
Yeah, so what when I write this proposal, ultimately I just hope to have let me just change back to my phone so that
Sure.
You guys hear me all right?
Yes.
Okay, great. Yeah, part of my experience in instrumentation. Well, yeah, so this project that we're hoping to is to investigate on different methylamine photodissociation product that we might be able to find with the Dragonfly mission in Titan. And this will be just very helpful information to build like a chemical model to see how these methylamine photodissociation can lead to the formation of, say, glycine or other complex amino acids. And with the best case scenario, we'll be able to collect all the spectroscopic data, and we'll hand it to some collaborators to build chemical models and hopefully to guide the future mission when it actually happens. And also just to want to add up to the previous question, I just did a quick calculation on the magnetic field that will be generated out with our DC voltage source. It will be about 0.25 microtesla with our DC voltage source. And just for reference, the Earth's magnetic field is about 50 microtesla. So it's comparing 50 microtesla to 0.25 microtesla. So I believe the impact with our DC voltage source will not be very significant comparing to Earth's magnetic field.
Okay. Awesome. Thank you for both of those answers. Okay. Do we have other questions from the audience? Everything was just so clear that everyone knows exactly what's going on. This is great. Yeah. All right. Well, if we don't have any further questions, then I just want to thank our speakers again. So thank you, Susanna, Ruby, and Hal. Those were fantastic talks. Thank you all to those of you in the audience for attending. And stay tuned for an announcement about when our next PC3 seminar will be. We'll keep you updated through the various channels, the Twitter, the emails, and yeah, the mailing list. So thank you again, and we'll see you in the near future.
Thank you for hosting.
Thank you guys for speaking.
Thanks, everyone.